prove that square root of 2 is irrational? Well, you know, a number is irrational when we cannot express it in the form p over q, or that number has a non-terminating and non-repeating decimal expansion. That means if you expand this number decimally, then you can show that this number actually has no pattern in its decimal expansion and just never terminates. So this number is going to be irrational, and it's going to take a lot of effort for you to prove that this number is irrational by showing it through decimal expansion. But we can prove that square root of 2 is irrational by some other method too. Well, not directly that square root of 2 is irrational, rather by contradiction or by negation, that because square root of 2 is not rational, it is going to be irrational. Why? Because we know real numbers are of two types. Either they can be rational or irrational. So if a number is not rational, then the number will be irrational. And that's what we are going to do here. So we will assume that square root of 2 is a rational number. So if square root of 2 is a rational number, then we should be able to express it as a over b. And here a and b are going to be positive integers because square root of 2 is positive, and even if a and b are negative, they would cancel out each other. So let's say that a and b are positive integers, and a and b are never going to be 0 because it has to be equal to square root of 2. So these two numbers are never going to be 0. Now I can write this expression as a equals to square root of 2 times b, and if I square both the sides, then I get a square equals 2 times b square. Now notice here, this number b square, or number a square, is 2 times b square. So a square is a number and then b square is a number, and the number a square is 2 times the number, some other number, which is b square. That means a square is even because the number a square is 2 times some other number, which is b square. So a square is going to be even, and if a is even, if a square is even, then a is also going to be even. I mean, you can have a square of a number even when the number is itself even. Otherwise, if it's odd, the square would be odd. So a is even, and if a is even, then you can write a as 2 times some other number, right? So a, let's say, is 2 times some other number p. Now let's square both the sides of this number. A square is equal to 4 times p square, and a square, you know from expression 1, is 2 times b square. So we'll replace a square with b square, which is 2b square equals 4p square, and 2 will cancel out 4 here by 2. So b square is going to be 2p square. Now I can apply the same reasoning here. Since b square is even, then b is going to be even. And if b is even, that means I can express this number as 2 times of some other number because this number is even. So b, let's say, is 2 times q. Let's say this is expression number 3. And now we want to calculate what is a over b. So a over b is going to be, a is 2 times b and b is 2 times q, which is p over q. That means I can simplify a over b to p over q. Now let's see b equals 2 times q, and let's square this expression. B square is equal to 4 times q square, and b square, you know, is 2p square from here. So I'll replace this with 2p square, and I get p square is equal to 2q square. That means p is going to be even, and if p is going to be even, that means I can write it as 2 times some other number. Let's say that number is r, and let's square this number, square this expression on both the sides. So it is going to be p square equals 4 times r square, and p square, you know, from here is 2 times q square, so q square is going to be 2 times r square. That means q is even, and q, if q is even, then I can write q as 2 times some other number, and that other number is s. Let's say s here. Now let's calculate what is p over q, which is 2 times r over 2 times s, which is going to be r over s. That means this expression can be further simplified to r over s. Look at the chain of simplification here. It's over b to p over q to r over s. Now take this expression q equals 2 times s, and let's square it both the sides. So it is going to be q square equals 4 times s square, and q square is 2 times r square. So 2r square equals 4 times s square, and that implies that r is 2 times, r is even, and if r is even, then let's say it is 2 times some other number, which is 2 times t. And then similarly you can show that s is going to be even and s is going to be 2 times some other number. So you can then calculate r over s, which is going to be 2 times t over 2 times u, which is going to be t over u. And you can repeat the steps over and again and have a chain of this simplification going on forever. I mean, you just keep doing it, and you will be getting a new value or a new ratio that is further simplification of this, of the original one. This is a over b. So this expression, you can say, will be v over w, and you can keep doing it like this and express it in terms of some other ratio. Now if you look at a over b, which are positive integers, and even if these numbers a and b have, let's say they have common factors, and if you put these numbers a and b in terms of the product of its primes, that means you apply the fundamental theorem of arithmetic, then the common factor would cancel out each other, and you will have a over b simplified that cannot be further simplified. That means maybe a over b is not simplified, but as long as these values are integers and you can express them as the product of primes, then you can always, if you simplify it, then you will always stop somewhere. Means its simplification will stop, not like here, which just doesn't stop. It keeps on going forever. So that means this number, square root of 2, which we assume that is a rational number, it's not behaving like a rational number, because I can always simplify this number into some other number or some other ratio, which is not possible for a rational number. It will stop somewhere. That means if this number is not rational, and if this number is not rational, that means this number is an irrational number, and that's what we had to prove. Let's see one more example. Prove that 6 plus square root of 2 is irrational. So we will use the same line of reasoning, which is, we will assume that the number is rational, and then we will get to a conclusion that the number is not rational, and that's why we can say that the number is irrational. So we will assume that 6 plus square root of 2 is a rational number. That means I can express this number as a over b, where a and b are going to be positive integers. A and b have to be positive because the term on the left side, that is 6 plus square root of 2, is always going to be positive. And a and b cannot be 0. If a is 0, the term on the right side becomes 0, and if b is 0, then the term becomes infinity, and both the values do not match up with the value on the left side, which is 6 plus square root of 2. So a and b are strictly not 0. Then I can write this expression square root of 2, this expression as square root of 2 equals a over b minus 6, which I can further write as a minus 6b over b. And if you look at this term, then it's a, which is an integer, minus 6 times b is an integer, over b, which is an integer, we know. So this is going to be an integer minus 6 times an integer over an integer. So it's going to be an integer over an integer, which is going to be a perfectly rational number. But the number on the other side, which is square root of 2, and we have already proved this, is an irrational number. And in an expression where both the sides have to be equal, how can one side be irrational and the other side be rational? Either side, I mean, both of the side either should be rational or irrational. We cannot have an irrational number equal to a rational number. Well, we have a contradiction here. And why do we have this? Why did we get this contradiction here? Well, we can go back to our assumption, or that's where we started working out this problem, by assuming that this number is a rational number. And if this assumption were true, that this number is rational, then I should have gotten consistent results. That means I should have both the sides rational, not irrational. Rational because that's what I assumed, but that's not the case here. So if this assumption is not true, which is that the number is rational, then the number has to be irrational, because a number or a real number can either be a rational number or an irrational number. So if a number is not rational, then the number will be irrational. And that's why I can say that 6 plus square root of 2 is an irrational number.